join in. All right. So welcome to today's ICANN seminar. It's our great pleasure today to have Jordan Cotler from Harvard University here. Jordan is currently a postdoctoral research fellow, part of the Harvard Society of Fellows. Before that, he did his PhD at Stanford and his undergraduate at MIT, so only good places. I think he's a Hertz recipient, and he's really an expert in all things high energy and quantum information science, which is a really exciting intersection. And yeah, without further ado, please.
Well, thank you so much for that nice introduction and for giving me the opportunity to speak. So today I'm going to tell you about emergent holographic forces from quantum circuits and criticality. And this is based off of some joint recent work with Rahul Sahai and Misha Lukin, who are both here at Harvard. So before launching into the details of the particular results of this work, I want to make some broader conceptual remarks that may pertain to people's interests in this group. So right now, at circa 2024, we're about 100 years out from the development of quantum mechanics. In particular, in 1924, de Broglie established his wave-particle duality, or at least suggested it, followed by 1925 and 1926, the development of Heisenberg's matrix mechanics and Schrödinger's wave equation, respectively. Now, I think it's quite interesting that we are presently at a moment where we're 100 years out from quantum mechanics, in which, aside from understanding its foundational questions, which took a lot of the last 100 years, that we're now interested in more higher level questions or even applications of quantum mechanics, especially with the advent of quantum computers and related quantum devices. We want to know how quantum mechanics and our understanding of it can be pushed both in the context of technology to help us understand theoretical constructs like quantum field theory using new kinds of tools. And I think that now is a very exciting time, even in this rather mature subject. So I want to highlight two prescient papers by Feynman from 1981 and 1984, respectively. One of them was Simulating Physics with Computers in 81, and then in 84, Quantum Mechanical Computers, in which Feynman envisioned and identified the key role for future quantum computers. So I've excised two quotes, which I think are emblematic of his theses in these articles. Feynman says, "The full description of quantum mechanics for a large system," by which he means, say, a quantum many-body system, "cannot be simulated by a normal computer." Of course, this was to him an assertion. He only had heuristic arguments for this, but now this is a claim that we would be very sympathetic towards, that for large quantum many-body systems, we certainly believe, due to the exponential size of Hilbert space, that simulating their dynamics, for example, Hamiltonian dynamics, should be possibly exponentially hard in generic cases for a classical computer, and as such, we need new resources such as a quantum computer. So Feynman, anticipating this, asks, can you do it, meaning quantum many-body simulation, with a new kind of computer, a quantum computer? You can simulate this with a quantum system, with quantum computer elements. It's not a Turing machine, but a machine of a different kind. So what I find very impressive about this is not merely that he has the idea of a quantum computer, but that he correctly identifies what the salient questions are of what one should do with a quantum computer, or even what the salient theoretical questions are, hinting at ideas about computational complexity. So in the present day, quantum computers now have hundreds of quantum bits and are expected to exceed the capabilities of traditional supercomputers in performing certain kinds of algorithms. And this, in a certain sense, is a culmination of Feynman's vision, ultimately, of being able to establish that there are certain kinds of computational tasks involving many quantum degrees of freedom, which quantum computers can do, but which classical computers are believed to be unable to do. I think, however, that as physicists, that the presence of these kinds of experiments, or even their possibility, should give us pause and should make us think carefully about what it has to say about systems that are near and dear to our hearts. So for example, if in the context of condensed matter physics, if we just have some quantum material, here is a chunk of bismuth, for example, looks nice and shiny, that if it's hard to say things about a contrived system of a few hundred atoms, then you might worry that there are certain features of systems in the physical world, such as quantum materials, which are also impossible to approach using standard theoretical tools, either classical simulation or even the means by which we write down equations to describe what a quantum material is doing. That is, the complexity inherent in certain kinds of quantum tasks uh, should also confer a difficulty in understanding generic quantum many-body systems, such as the ones that we study as physicists. So here is also, one can also ask more specialized questions about, for example, atoms and optical lattices, or systems which are much under greater control in the context of AMO physics, but for which it is easy to ask questions about natural Hamiltonian dynamics, which are well beyond the scope of what any classical computation or simple theoretical equations can provide. So let me make two claims, which I will discuss one of them in this talk. One is that quantum computers can or will be able to unlock aspects of nature which are inaccessible to conventional experiments. So this is to say that I think that quantum computers are going to allow us to probe natural systems in ways that are otherwise impossible with our usual paradigm of merely preparing some quantum many-body state or system, measuring it, collapsing the wave function, and then collecting ordinary classical statistics. I think there's a richer set of possibilities which is afforded to us by coupling quantum computers to natural systems. The second claim is that I think that quantum information can be used to explain a wide range of physical phenomena. This is maybe a less controversial statement. I assume that many of you are here because you believe in this second claim, that quantum information provides us with a wide variety of tools to understand condensed matter systems, quantum many-body systems, and quantum gravity as a nice recent example of many explorations. And what this suggests is that there is a set of connections between quantum information, computer science, quantum gravity, and quantum many-body physics, which allows us to unlock new kinds of synergies that will mutually benefit all of these subjects. So I think this is the emerging frontier of theory in the area of quantum information, is understanding how our understanding of the laws of physics in quantum gravity and quantum many-body physics are informed by a more algorithmic or information theoretic perspective. And this is what I'm going to pursue in a particular example henceforth in this talk. So what do I mean by the interplay between quantum information and quantum many-body systems? So here is a cartoon. Here on the left is a picture of a quantum circuit. On the right is a picture of, some interacting quantum many-body system. Well, there are many areas in my own work and the work of other people in which the language of quantum circuits, algorithms, computational complexity, and entanglement is used or interfaced with the more conventional language of particles, forces, fields, symmetry, and space-time. And the example that I'm going to show you in the next few slides is going to be an example in which what would otherwise appear to be a conventional example of a gravitational system that would be describable in terms of fields and symmetries in space-time will have an underlying description of quantum circuits and entanglement and algorithms, which will explain some of the properties that we see from an ordinary physics point of view. Let me maybe skip talking about some other examples in which these kinds of connections have been fruitful. So we're going to consider a particular framework for understanding quantum gravity known as the ADS-CFT correspondence. So let me summarize in a nutshell how the ADS-CFT correspondence works. It stipulates that there are certain kinds of theories of string theory or types of quantum gravity that live in so-called anti-de Sitter spacetimes. You can think about these as spacetimes with a certain kind of negative curvature. So again, you can think about this as just strings or particles or what have you interacting, including the fundamental degrees of freedom of space-time itself. And on the other hand, that there's a remarkable duality discovered by Maldacena of these kinds of systems to conformal field theories. Conformal field theories are just more akin to ordinary quantum field theories with enhanced symmetry, and they do not furnish quantum gravity. These are theories that are devoid of gravity and that are under much better theoretical control. So the reason that this kind of duality is interesting is it tells us that if we want to understand certain features of quantum gravity, which we might be very interested in about fundamental questions about space and time, that it suffices to have a deep understanding of conformal field theory, and moreover, the mapping between phenomenon conformal field theory to phenomenon ADS by virtue of the duality. So a problem, however, is that, as promising as this may seem in principle, there are many features of anti-de Sitter quantum gravity which are inaccessible with the standard methods of ADS-CFT. There are a variety of reasons for this. One is that standard ADS-CFT examples require supersymmetry, strong coupling, large N, and large central charge. Some of these features help the analysis of ADS-CFT, others hinder it. But what I would say is that because fundamentally the nature of the map between the conformal field theory and the gravity theory is not perfectly understood, and the fact that the conformal field theory is in many ways a very complicated type of object, for example, due to strong coupling, this limits our ability to have a window into the nature of anti-de Sitter quantum gravity that would otherwise be provided by the duality. So an idea which people have had for a while in various forms is, okay, well, if the difficulty of conformal field theory is similar to the difficulty of just simulating a quantum many-body system, well, we should use a quantum computer, as Feynman has told us. That what we should do is we should simulate the ADS-CFT duality on a quantum computer using, for example, a critical spin chain as our proxy for the conformal field theory. So that is, if we can simulate the CFT, well, a quantum computer doesn't care about strong coupling, or that's totally fine. And if we have a good handle of what the mapping is between the CFT description and the ADS description, then this should enable us to unveil aspects of ADS-CFT which were hitherto unknown. However, to achieve this, really there are two big lurking questions. First, we need a quantum circuit which implements the duality map between the conformal field theory and the ADS description. Doing so is either at the edge or beyond the edge of our current understanding of ADS-CFT, depending on in what detail we want to render this circuit. The other question lurking is, well, can we even, given the fact that we're doing all of these approximations, that we want to approximate a CFT by a critical spin system, and there's finite size issues, and there's a lattice scale, that can we even fruitfully reproduce predictions of ADS gravity by means of such a quantum simulation? That there's so many potentially difficulties and tactical retreats that we need to make in order to do such a quantum simulation. Do they muck up the results that we would otherwise want to see? So what I'm going to suggest, by virtue of this recent work with Rahul Sahey and Misha Lukin that came out this year, is that there is a path forward, that there are ways of constructing in explicit examples quantum circuits implementing a duality map between a CFT description and an ADS description. And moreover, that this framework reproduces features of ADS gravity, which should be able to be corroborated by contemporary quantum simulators. So that's what I'm going to explain to you in the rest of the talk. So let me mention one other feature of ADS-CFT, which is going to be important going forward. I'm not sure if you can see see the video, because I'm going to, I have a prop. So one of the strange features of ADS-CFT is that the ADS theory exists in one higher spatial dimension than the conformal field theory. So that is to say that if you have a conformal field theory, for example, in 1 + 1 dimensions, you can imagine it, for example, on a circle. So that's a one-dimensional spatial slice, and then it evolves in time. Then the ADS theory will have one higher spatial dimension. It'll have two spatial dimensions and one time dimension. So across this duality, one of the dimensions of space is emergent. So I have here some kind of Hallmark card, and if you take this card, it's two-dimensional, and you open it up, you suddenly see that it becomes three-dimensional. And that's the surprise of ADS-CFT in a certain way. It's that this higher dimensionality is somehow folded up inside this lower dimensional conformal field theory, that you're getting this extra spatial dimension worth of data, which is folded in a certain way inside the conformal field theory. So one should keep that in mind for the examples going forward, that we're mapping from a lower dimensional theory to a higher dimensional theory when we go from CFT to ADS. So here is a picture of the Escher disk. This is what a spatial slice of 2 + 1 dimensional anti-de Sitter looks like. So this is to say it's what it looks like at fixed time. That by virtue of the constant, but by virtue of the negative curvature, we see that it looks like these birds or fish or whatever Escher was drawing look smaller near the edges of the disk. And what we're going to do is to construct a map between a one-dimensional state of the conformal field theory, or rather a critical spin chain, and a map between that and a two-dimensional state, which is going to correspond to a proxy for the anti-de Sitter bulk. So here's the ground state of our, this is a tensor network diagrammatic representation of the ground state of a one-dimensional ring, where each of these little lines corresponds to qubits. And we're going to suppose, as our particular example of a critical spin chain, that psi sub gs for ground state is the ground state of a Z2 cross Z2T enriched Ising CFT at long distances. So that might sound fancier than it is. It's just this Hamiltonian, which furnishes certain discrete symmetries, the product over Z's, as well as a complex conjugation operator. And the reason that we choose this particular enriched Ising CFT will become apparent in a moment, but it's that it admits a relatively analytically tractable tensor network representation for its ground state. So that's why we choose this one in particular. It's out of theoretical convenience, although I suspect that a lot of the lessons that I will confer are not specific to this particular type of spin chain, that I think any critical spin chain will suffice. So what we're going to do is we're going to build a quantum circuit, which we can think about as a unitary which acts on this state. Here I've drawn it in this tensor network diagram, which is going to map this one-dimensional state into a two-dimensional state, where the qubits of the two-dimensional state correspond to the dangling legs in the bulk. In particular, it turns out that there is a mapping, U, which approximately maps the ground state of this enriched Ising CFT to the product over all zero states. Sorry, the tensor product over qubits in the zero state, which we're going to take as being a proxy for the bulk state. So the particular nature of the map that will bring us from the ground state to the product state over all zeros is going to be a Mera tensor network, which was originally developed by Guiffre Vidal around 2006. And it instantiates a form of what's called entanglement renormalization, which you can think about as a version of real space RG, renormalization group, but for quantum states. So if you wish, it's like a quantum version of Kadanoff block spin renormalization group. So let me explain to you how these kinds of circuits work. What you do is that you take the entangled conformal field theory ground state. Here I've unwrapped the circle and just drew it on a line segment. And then in the first layer of the circuit, what you do is you remove short distance entanglement by these local unitaries. These objects, which take in 2 qubits and output 2 qubits, are referred to as unitary disentanglers because of the entanglement which they so remove. Then, after having removed some of the entanglement, what you do is that you apply a unitary distiller and coarse grainer. What this does is that it takes in 2 qubit degrees of freedom. It tries to extract a 0 qubit, and then it lets the other remaining degrees of freedom go on their merry way. So you can view these two steps of the circuit as a form of decimation, where we are extracting these 0 degrees of freedom and letting some other degrees of freedom go on. But the number of degrees of freedom which survive, which are not sort of in the form of 0 qubits, is half of the number of qubits which were inputted. So we see that 1, 2, 3, 4, 5, 6 qubits go in, 3 are distilled as zeros, and then only 3 continue on in the circuit. And this process then can be iterated and so on until you've essentially decimated everything. You've just extracted a bunch of 0 qubits everywhere, and that's represented here in this diagram. So we see here that there's a kind of hyperbolic disk structure to the mirror tensor network that, because of the fact that the number of degrees of freedom that are effectively decimated is exponentially decreasing as a function of time, that there is a correspondence between the graph of the tensor network, of the mirror tensor network, and that of the hyperbolic disk, which is at least suggestive and has inspired various people, maybe most prominently, say Brian Swingle, to suggest that there are features of the map between the ground state of a critical spin chain and the corresponding bulk state, which are emblematic of ADS-CFT, although we will make this precise in a moment. Going backwards, we could suppose that we start with a proxy for the ADS bulk state, that is these zeros. Suppose that we turn one of the zeros into a 1. We're going to think about this as a type of bulk excitation. That's like turning on some matter degrees of freedom in the bulk. And running the tensor network in the opposite direction, or running the circuit in the opposite direction, this 1 will end up imbuing an excitation on top of the ground state, that it'll modify the ground state. So this is to say that if you create excitations in the bulk and you push them back through the circuit to now get a state of the conformal field theory, it'll correspond to, again, the ground state plus excitations on top of it. So we're going to do that over here, and instead of just merely creating 1 excitation in the bulk, we'll create 2. So we'll turn 2 of the zeros into 1s, which we'll think about as chunks of matter which are going to live in the bulk. And then we're going to push that out to we're going to apply the circuit to map from the description of the ADS bulk to the 1+1 critical spin chain, which will then give us the ground state with 2 excitations on top of it, which will be the CFT proxies for the bulk excitations. So what question might we want to ask about this? Well, a very basic question we could ask about this to see if anything that we're discussing is at all like the ADS-CFT correspondence as opposed to a very toy model thereof, is we would like to check if the 2-particle interaction of these 2 excitations matches the predictions of, say, general relativity with coupled to matter in anti-de Sitter space. So that is to say that I said that there was some analogy between creating these excitations in the bulk and something about anti-de Sitter space. You might ask, is the effective potential generated by putting these 2 particles in the bulk the same as you would predict for 2 particles in anti-de Sitter space that interact by virtue of gravitational attraction? So that's what we're going to check. So in order to match a tensor network result to a gravity result, we have to do a gravity calculation. So let's suppose that this is this represents anti-de Sitter space at a fixed moment in time, and that we create 2 excitations at radial coordinates ρ1 and ρ2, and we want to measure their effective interaction potential. So this is to say that we take the energy of the particles at ρ1 and ρ2 together and subtract off their individual energies. So we're just extracting the interaction potential. And we want to compute this in the background of anti-de Sitter gravity, or an anti-de Sitter spacetime. So we're going to consider at first a slightly simpler result, which is that we're going to move one of the, by a coordinate transformation or by a boost, we can move one of the particles to the origin of anti-de Sitter space, and then the other one is situated at radius ρ1 minus ρ2. This will just make the answer slightly simpler, and then we can go back to our other coordinates in a moment. So what's the slickest way to compute this? Well, first, let's recall a calculation that's not an anti-de Sitter space, that is maybe in the more familiar setting of black holes in 3+1 dimensions, that some people may remember from taking a course in general relativity. If we write down the Schwarzschild metric in 3+1 dimensions, here it is, r here is the radial coordinate. And if you put a test particle or a probe in the Schwarzschild background, in the background of a black hole, this is the energy which it has as a function of radius. And if you do an expansion at large radius, you find that there is an initial term, which is just the energy of the particle, equals mc squared, of the single particle energy. And then there's an interaction potential, which you can think about as the interaction between the particle and the black hole at the center. There's, of course, other corrections, but it's nice to see Einstein and Newton coexist in a single equation, at least, which, of course, is the dominant physics at large radius. So we can do the same calculation in the context of ADS. The salient metric is the BTZ metric, where now rho is the radial coordinate. You do the same kind of computation, and you find that that E of rho, the energy of a particle in the background of another one at the origin, has this form as a function of rho, which if we expand it, for example, in the regime that rho is much larger than L, where L is actually the curvature scale of ADS, that we get this result, where we can think about this term is the single particle energy, just the energy of a particle in ADS by its empty ADS. And this second term is the interaction potential between the two particles, which we see goes as 1 over cosh. So therefore, we expect that, at least in what we've shown by this calculation, is that the gravitational potential between two particles, one at the origin and one at location ρ1 minus ρ2, is equal to this blue quantity. So let me record that over here. Now, if we do a boost to move one of the particles to ρ2 and the other one to ρ1, we incur this extra boost factor, which, well, it is what it is. It gives us some extra dependence on ρ1 and ρ2. So this is actually the full form for the potential in the regime that the separations are much larger than the curvature scale. Okay, so now let me expand this in the regime that they're much larger than the curvature scale. Just the answers simplify slightly. We get this nice functional form. And let's now compare this with numerics for the quantum circuit. So again, the right-hand side of the slide is the result of a gravity calculation, a calculation in general relativity. And the left-hand side is a result of quantum circuit numerics for this Ising spin chain, where again, we took the Ising spin chain, we mapped it into a bulk description using a tensor network. We created two excitations, mapped it back to the Ising description, which now is like the Ising model ground state with two excitations. And then we compute the interaction potential using the Ising CFT Hamiltonian. So this is what we get. So this is the answer for, as we vary, for fixed ρ1 minus ρ2, as we vary ρ1. So it's not obvious that this answer looks at all like the gravity answer. But it turns out what's useful to do is that if we wanted to get a simple function of ρ1 minus ρ2, what the gravity answer would indicate is that we should divide by this red term. So the blue term just depends on ρ1 minus ρ2. The red term does not. This is a boost factor. So what this suggests is that if this is equal to this, then if we divide by min ρ1, if we divide by this min factor, then all of these curves should collapse, and we should get a nice potential that only depends on ρ1 minus ρ2. So lo and behold, if we do so, if we divide by the boost factor, we see that beautifully all of our curves collapse, indeed, which are a function of ρ1 minus ρ2. And in fact, we find that there is an attractive force between the particles which matches the form of the ADS prediction. And one can do a more quantitative matching, especially at the tails, which corresponds to the nature of the attractive force at distance scales which are much larger than the curvature scale. So this is nice. We see some signal that even in our toy model of holography that it knows something about the nature of the attractive force. But now we would like to have a deeper understanding of what's going on here. Why is it that our toy model should know something about this attractive force endemic to ADS gravity? So what we've shown so far is that there's a quantum circuit implementing entanglement renormalization, which knows something about the attractive gravitational force in anti-de Sitter space, at least in 2+1 dimensions. Now, the question we want to know is, how does the quantum circuit know about gravity in detail? Why does it seem to produce the detailed form of the potential at long distances? So there are two components to this. There's this attractive gravitational force, and then there's also this gravitational boost factor that I explained. Those were the blue terms and the red terms in the equation. So in fact, I'm going to explain to you how both of these phenomena arise from a quantum circuit picture, which we detailed in this paper with Rahul and Misha. So here now is the quantum circuit, which describes the perturbed version of the ground state of the ISO model with these two bulk excitations. And what we're going to do, because it gives us the easiest means of analysis, is consider entanglement renormalization in the Heisenberg picture as opposed to the Schrodinger picture. So we're going to see how operators evolve under entanglement renormalization to give us a handle on why these gravitational potentials should arise from a tensor network analysis. So what I'm going to do is I'm going to take this excitation, one of the particle excitations, and I'm going to push it out to the boundary on the circuit. So this is what happens when we push it out to the boundary. And then I'm going to consider a Hamiltonian, because we want to measure the energy, which is the Hamiltonian of the enriched Ising CFT. And then what we're going to do is we're going to take the Hamiltonian and take the operator, and we're going to push them into the bulk. So we can think about the Hamiltonian in a tensor network notation as a sum over these local operators. So H sub s is the Hamiltonian density, if you will, around site S. And we're going to ascend it through the network. So we're going to, in the Heisenberg picture, perform this entanglement renormalization on H and push it up through the network. And when we do so, when we push it up through one layer of the network, it's equivalent to applying this kind of ascension superoperator onto H. And then we can iterate this k times if we want to move it up k levels of the network. So we can think about this ascension superoperator as a coarse graining map, which encodes CFT data. You should think about it as like a step of RG, but applied to operators. Now, there are various things one can say about this map, but one is that its singular values are scaling dimensions of primaries and descendants of the Ising CFT. So this coarse graining map, as you might expect, knows something about the CFT data. So when you push this thing up through, when you push the Hamiltonian up through the network, what you find is that there's a contribution from the identity, as well as a contribution from the stress tensor in the CFT language. And the contributions of the stress tensor, the coefficient in front of it depends on how many steps you do RG. Here I've done k steps of RG. So what we do is we, as advertised, we take H, we take this operator, and we're going to ascend them to the level of the network where they're at the same layer as the second excitation. So we do that. So we ascend them. And the answer that one gets is that a quantum circuit calculation along the lines of just thinking about the algebra of these ascension operators gives rise to an expression for the two-particle potential. So here's what you find. So you find that there are two pieces. First of all, you find that by doing this quantum circuit analysis, you get this gravity boost factor just as part of the answer. This comes along with doing the quantum circuit calculation. It reproduces precisely this gravity boost factor. Now, the first term is a little bit richer. It turns out that this first term is a sum over, so alpha labels primaries and descendants with the exception of the identity. And it turns out that the leading contributions to this include a coefficient or a constant that comes from the epsilon primary, and then another term that comes from the holomorphic and anti-holomorphic parts of the stress tensor, and then the descendant of also the epsilon primary times this exponential factor. And what you find is that the stress tensor contribution is large and negative, whereas the contribution of these descendants of epsilon are very, very small and hence can be neglected when you do the computation. So as such, this approximately equals this expression. There's a contribution from epsilon and there's a contribution from the stress tensors, which is negative. And then putting this all together, moving it up here, we see that these contributions here from the quantum circuit calculation reproduce the form of the gravity answer. So again, these coefficients are order 1 and negative, which looks like the precise form of the attractive gravitational force. And there's also a term up here, which is, if you will, a part of the interaction potential that arises because of the epsilon primary. So we see that the contributions of the stress tensor in our quantum circuit analysis match the form of the attractive gravitational force. And for those who think about ADS-CFT, the fact that the stress tensor is, in a certain sense, dual to physics of gravity should be no surprise. That's an ordinary ingredient in the ADS-CFT dictionary. But what's nice here is that we see, by virtue of a quantum circuit calculation, that the form of a quantum circuit calculation gives rise to the same form of the gravitational attractive potential expected in 2 + 1 anti-de Sitter. And in fact, we can do a quantitative matching of this expression to our numerics, and indeed, it agrees well, because this is a quantum circuit calculation. This is just a numerical version of the same calculation. And as such, we can explain both the attractive gravitational force that comes from these stress tensor contributions from the point of view of this quantum circuit calculation, as well as this gravitational boost factor, which also comes out of the quantum circuit analysis. So as such, we have taken two features that we have seen by a general relativity calculation, these two terms, which again we got by doing GR, and we have found them in a very different way using a quantum circuit analysis inspired by a quantum real space version of the renormalization group. So let me conclude, since we're at the end of our time. So the idea of this whole setup, or the motivation that I mentioned, was to use quantum simulators to explore gravitational dynamics, or really ideally features of the ADS bulk theory, the ADS-CFT correspondence. So the kinds of questions which you might be able to answer with these kinds of toy models, or at least get insight into, is the question of, why do objects fall? This is a question, I think Lenny Susskind phrased it this way. Can we understand from a quantum circuit point of view why objects in the ADS bulk tend to fall under gravitational dynamics? And I think that some interesting extension of the quantum circuit techniques, which I alluded to in the previous slides, could give us a more detailed conceptual and technical handle on not just static properties of the bulk, but dynamical properties of the bulk. Now, a natural platform to explore these ideas includes programmable Rydberg arrays, one which, of course, is close to Misha Lukin's heart, because that's what his lab does. But these programmable Rydberg arrays are particularly nice for instantiating these tensor networks, because they have the ability to rearrange the configurations of the atoms in space without significantly degrading their mutual entanglement. So this is a virtue for trying to do tensor network circuits in which you really want to hierarchically maneuver and manipulate the qubit degrees of freedom, so to entangle them according to this hierarchical quantum circuit. So the basic picture, just to sketch it as to what an experiment would look like, is that you would initialize some two-particle state of, you take the Ising ground state, which you can prepare by various means, and create these excitations on top of it, which would correspond to two bulk ADS particles. You would then time evolve this state using the Rydberg Hamiltonian, which can be tuned to Ising criticality. And then you would perform the tensor network circuit to read out the state of the bulk. That then would tell you essentially how the bulk state has evolved dynamically. And this is now a cartoon of what the circuit would look like if you needed to do it on the Rydberg array. So to summarize and to make some broader final remarks, so quantum computing and quantum information inform many subjects, including condensed matter physics and quantum gravity. And moreover, the tools that I have brought to bear on the ADS-CFT duality in this talk combine ideas from quantum information, condensed matter, and quantum gravity. And I think that it's exciting that these different tools can cohabitate in these kinds of analyses. So I think that quantum computers can help us unveil previously unknown aspects of nature, which may in turn require quantum information to describe, for example, in the context of quantum gravity. And I think that going forward, the ability to leverage quantum computing and quantum information is going to bring theorists and experimentalists together from diverse areas of physics to reach new scientific frontiers and help us teach us new and exciting things about the ADS-CFT correspondence, about strongly interacting quantum many-body systems, and many other fascinating physical phenomena. So with that in mind, thank you so much for your attention. Happy to answer any other questions in the discussion portion of this of the talk. So thank you.
Well, for this very insightful talk. We have plenty of time for questions. Anybody have a question? Also, online, just unmute yourself if you have a question. Actually, I have a question. So, oh, Henry. Okay, there's Henry. Yeah. Go ahead.
Hi, thank you. This is a very interesting talk. I had just a quick, small kind of technical thing.
Yes.
One of the first when you're just introducing these excitations and you say on the boundary state, it's this O prime times your CFT ground state.
Yes. Yeah.
So do O and O prime commute? Because just in my head, the way I think about this is you add excitations on the gravity side. It shouldn't matter kind of in which order you add them. But in principle, O and O prime, depending on how you like create these excitations, it could change things on the CFT side.
Oh, well, I mean, one way of seeing it is the preservation of commutation relations under unitary equivalence. Is that if you take two operators that commute and you conjugate them with a unitary, they'll still use and U dagger will cancel. Does that answer your question or?
But you're saying that they do commute, correct?
Yeah, at least in this case they do.
Okay. Okay, thank you.
I mean, let's put it this way: they commute because the bulk operators, they're just spin flips. They're just poly X's on different sites.
Okay. Okay, thank you.
Sure.
Yeah, maybe last. Do you think this setup is useful to simulate states that would be dual to black holes or more complicated gravitational backgrounds than ADS?
That's a good question. I mean, you could ask what happens if you create a chunk of excitations in the middle of the tensor network, but let me maybe make one other remark about why I think this is interesting, even from a pure ADS-CFT point of view, that I didn't say during the talk that might be of interest, which is that something that we struggle with in ADS-CFT is understanding. There's something that we say that's hard to precisely substantiate, which is that in global ADS, that the radial direction is the RG direction. Now, except by maybe these papers by Polchinski and collaborators from maybe 2011 or various other follow-ups, it's actually hard to make sense of that non-perturbatively, like what we mean by the bulk direction being the RG direction in global ADS. Of course, in the Poincare patch, it's an easier story. So what I think is going on here, or part of the reason why this is working, is that in a certain sense, I think that the mirror tensor network is like it's a mirror tensor network which is designed for the Ising CFT. It's the one that produces the Ising CFT ground state. It's like a minimal version. It's like a non-perturbative lattice version of RG, which knows something about the CFT data by its construction. And as such, it's kind of like a non-perturbative, but nonetheless toy model of how you would interface some RG data into the ADS CFT dictionary. So I don't quite know how to make this precise, but I think that there's something I think to be understood about whether there's minimal data about RG schemes that are compatible with CFT data, which will allow us to extract new kinds of insights or do new kinds of calculations in ordinary ADS CFT in a controlled setting. I just wanted to throw that out there as a thought.
Just since you mentioned those papers of Pochinki, I assume in the dual of these models, you have locality on ADS scale.
Yeah, this is all super ADS scale physics, indeed.
Okay.
Yeah, so there's no sub-ADS locality, if that's what you're asking. Now, of course, well, there's a question of, well, I mean, I don't think we understand the dictionary well enough to even do that, but nonetheless, we don't expect it for the Ising model in any case. Sub-ADS locality, just string scales, the curvature scale, and so on.
Yeah, no, but okay, maybe it would be nice if, I don't know, maybe one can study some deformation of the model that will somehow, yeah, I don't know.
Yeah. That's right.
I saw there was a question by Jarun. Jarun, do you just want to unmute yourself? And well, there's a question in the chat. Maybe it wasn't Jarun, but somebody in the chat. Or maybe I'll just read it. Can you? Yeah, I'll read it. Can you explain again what the meaning of the yellow ket1 state becoming a yellow bar is in the diagram for the entanglement rate optimization?
Yeah, yes, absolutely. So let me just go to that slide. Hold on. So, okay. So there's a move. I assume this is the move right here. So all I'm doing is I'm taking this, so that you can think about this as a spin flip on one of the dangling legs. And all I'm doing is I'm pushing this operator through the tensor network in the Heisenberg picture to move it to the boundary of the CFT. So I'm essentially conjugating this thing by the dagger of the quantum circuit to just move. So in other words, this state is equivalent to this state. This is just a move of operator pushing this thing through the tensor network by conjugating it on both sides. I don't know if that helps answer the question. Good. Okay.
All right. Do we have more questions? Otherwise, if I may ask a question. So I was wondering how far can you push the mirror representation of the ADS CFT duality? Because let's say I'm interested in not a ground state on the boundary, but a highly excited mid spectrum state, for which if I restrict myself to a fixed bond dimension, I will have troubles writing down a mirror or tensor network, but presumably the correspondence will hold. Right? So is there something else that I can do?
Yeah. So okay. So let me mention. So something that I glossed over a bit is that the tensor network here is bond dimension 2 in this analysis. Now, again, in a certain sense, it only approximately gives rise to the ground state of the Ising, this symmetry enriched Ising CFT. And you can do better at if you fix the number of qubits, you can do progressively better by increasing the bond dimension. And what's nice is that there's these nice papers by Glenn Evenbley and others where they write down what the tensor network is in closed form, or like, in a certain sense, the best approximation of the circuit at fixed bond dimension. So as you increase the bond dimension, you can read the paper and it'll tell you what you should choose these tensors to be. So going to higher bond dimension should give a more quantitatively accurate version of this holographic duality or this toy duality. But to your point of, okay, well, you said, well, what happens? It's kind of like what Joaquin was asking. What happens if we look at these excited states where we put in like a black hole or something? Well, I think that would be very interesting. I mean, I think that some caution that we need to have is that since this is a toy model of ADS-CFT, it's not exactly clear how, if we push it more, in which ways do we push it? Will it continue to work? So I don't know, but I think that's an interesting question, which could be tested numerically.
Probably what Joaquin had in mind. So if I just put one black hole, right, then it's in some sense it's still a low energy excitation, and a tensor network will probably be able to do it. But let's say if I had a high energy like excitation. Right, then we know essentially that the bond dimension explodes exponentially.
Well, I mean, it depends exactly what you want to do. So something you could do, for example, is you could draw a circle around the middle of the tensor network and look at the qubits which you've circumscribed, and you could take them out and replace them with a highly entangled state, for example. And indeed, there would be, because of the fact that the mirrored tensor network is just a unitary circuit from these legs to the boundary, you can push that out to the boundary and you can see what state you'll get, and you'll get a very excited state of the Ising model. Indeed, there might be other ways in which it might be better to do this after increasing the bond dimension, but there's various kinds of games that one can play, and I don't yet know exactly what the most fruitful direction there is, except to think about the dynamics. I mean, to me, it would already be interesting, instead of just looking at static properties of these excitations, well, what happens if you evolve them? And that's not a question that we can answer with numerics, of course, because because essentially you get a blow up of the the parted Hilbert space you have to keep track of. So you really have to have recourse to a quantum simulator to even understand relatively basic dynamical questions about this setup. To my knowledge, maybe there's a clever simulation algorithm that we haven't thought of. That's possible, because a lot of this is related to like free fermions and Gaussian free fermion circuits, but it's sort of hard to get that to work for a variety of reasons efficiently.
Okay. Do we have any more urgent last-minute questions? If not, let's thank Jordan again.